Hi everyone, I'm Lehner. I'm going to be doing either 2 or 3 classes, depending on how we go. And what we're going to be trying to do today is just come up with a decomposition of the spacetime in 3+1 form. Later I'll tell you why this is just a particular case. We can do other things, but this by and large is the most useful in many fronts. And also try and understand how to reinterpret Einstein's equations in an evolutionary mindset. The idea is that if we know the state of the space-time at some given instance, whatever instance that might be, where we can actually define or understand how that's going to change to the future of that given instance. So imagine you have as you know, we're trying to go from kind of a manifold endowed with some metric that satisfies Einstein's equation and reinterpret this in kind of a constructed form. So we'll have some way, we're looking forward to having some way of reinterpreting this equation in terms of something that tells us how things change in time. So we need to introduce some sort of time in our space-time. We know that that's artificial, so that will then implies some freedom that will come with it, and we also want to recognize what it is and try and make everything explicit. So let's start with our manifold, our metric, and let's try to reinterpret that in a different way. So suppose, well, this blackboard is our manifold, and let's introduce some foliation labeled by some coordinate, let's say t, some label t, and then the next one says t plus delta t, and so on. Each of the leaves of the foliation, let's call it sigma. And of course, we have complete freedom on how we label points in our space-time. So let's imagine we have a point here, and at the next leaf, of course, this point would have coordinates t, and let's say x. And let's imagine that the next slice, and foliation, and leaf of the foliation, we give this point the same spatial labels. And of course, because we have chosen our coordinate or our label t to tell us something about time, this is going to be t plus delta t. Of course, the requirements of these leaves are space-like. So each space-like. Of course, we know each leaf is a space-like if it's normal, it's time-like. So let's consider the normal to this point. Let's call that NA. That's going to play a crucial role in our discussion. So let's imagine now that we follow that normal till we meet the next leaf, sigma t plus delta t. We have delta t will be in our way of labeling the surfaces. Delta t will be the time difference between the two leaves at these points that are joined by the normal. But we can ask, what is the proper time as we go along this way? Of course, that proper time, let me call it delta tau, will be related to delta t by some factor, which depends on whatever point we're thinking about. And that factor, we're going to call it alpha, and alpha is our lapse function. So it depends on each point, and it allows us to connect the time difference as measured or as determined by our foliation with the proper time. Now we also, once we land at this point, we would like to relate that point with a point that has exactly the same labels. We've got x here and x there. So we're going to introduce a vector here. We're going to call it bi. So beta I is the shift vector that takes us, as I said, from the point we land, if we follow it normally, tangent to the normal to the next leaf of the foliation, and the point that has exactly the same coordinate labels that we assigned to the previous point. Now let's think of another point here, which is at now at t plus delta t and x plus delta x. So we have and we want to measure the distance between this point and that point using what we have introduced. Well, we need one more thing. Let me call it gamma ij. It's the metric tensor at each sigma. So at each leaf of the foliation, we have an intrinsic metric tensor, which allows us to measure distances just on that hypersurface, on each hypersurface as we go along. So now we can determine this distance. So ds squared will be given by minus alpha squared dt squared. That measures that time. That this interval, we need to include that interval, and that interval will be given, so it's the distance on that leaf will be given by so notice here we're taking into account that we have delta x is this distance between that point and that point that have the same label as here, but we're moving all the way there. And then we also have to add that extra piece because alpha delta t is measuring only this interval. But of course, we started from a metric GAB, so now there is an easy way to relate the metric of the full spacetime and this decomposition we have introduced using this Laff's shift and the metrics that are intrinsic to each hypersurface. So now our metric, let's say we can write it this way. And the inverse is minus 1 over. So we're going to be introducing a whole bunch of definitions and formal relations using this framework that we're introducing. Any questions on this? So our goal, what we want to do is try to turn our understanding of the space-time in terms of a full four-dimensional, say, metric, and the equations of Einstein equations written that way as a subset of equations that we say if we know enough data on a given hypersurface, we can determine what the metric is at the next hypersurface if Einstein's equations are satisfied in terms of things that live or are naturally determined with respect to what is going on at each leaf of the foliation and these free functions, in principle, the lapse and shift that we're introducing. So notice that we can introduce already with what we defined so far, something we'll call a projector, which is going to be this relation. So if n is my unit norm, if my normal, I'm going to choose it to be normalized, so it's going to be uninormal. Orthogonal to a given hypersurface, we can define this tensor, which is the addition of the full metric tensor with the multiplication of that unit normal. So notice that if I have a vector that is orthogonal to my hypersurface, therefore is tangent to my unit null vector, my unit vector, if I multiply that vector on this metric, I'm going to get a 0. Because NA satisfies, given my signature, so it's unit normal. I'm choosing the signature is minus plus plus. N was orthogonal to a spatially hypersurface. And because of that, then it's time-like. And then the contraction of N with itself, given it's normalized, gives me -1. And so let's say in particular, if I multiply this by N, then N multiplying G will give me N again. But then here contracts with itself, gives me a -1. And so I have N minus N is equal to 0. For later purposes, let's introduce slightly related vector. So now let me just imagine that we're in 1 + 1 dimension, so we can do this easily. So, well, let me just do. So my normal vector NA, this was sigma t. This is my shift vector pointing this way. We have NA that is normalized in that way, so then NA has to be equal to minus in coordinates adapted to this decomposition now, if I define NA this way, because my inverse metric is given by that, then NA is normalized. And I choose this minus sign here because I want the vector to be pointing to the future. If I had a plus there and I raise it with that metric, I'm going to have a minus sign. So this is a vector pointing downwards. So that's that one. I can raise it with a metric, and now NA is given by so from here, we have this relation that d dTA is alpha. So the vector that is tangent to this line, which is normal to this hypersurface and is going towards the next one, is the dt can be written in terms of our lapse shift and the normal vector this way. Later on, we're going to use this vector, the dt, to naturally account for the rate of change of this metric, or the metric tensors that we're going to define from one hypersurface to the next one. So we need a little bit more information still, because what we have so far is the metric intrinsic to each hypersurface, 4 extra pieces of information, the lapse of shift that kind of allow us to relate this hypersurface to the next one, but we still haven't said anything about how this particular hypersurface is embedded in the larger spacetime. So if I think of this piece of sheet, this sheet of paper, this has naturally flat spacetime, a flat metric in it, but whether it's kind of embedded in this extra dimension this way or curved that way, we want to measure that somehow. So for that, we need another concept, which is that of extrinsic curvature. So we're going to introduce it in a very kind of simple way. We're going to say, well, consider n, and we want to measure how n varies if we parallel transport it on this given hypersurface. And in particular, we want the projection on this hypersurface itself. So whether n, as it's translated to kind of a near point, points in a direction different from the normal that we measure at this point, that's something we want to measure. So if we parallel transport, this vector might point in that way, while this one would have pointed this way. So the extrinsic curvature will be measuring precisely how the way this hypersurface is curved in the embedding spacetime behaves. So we define this extrinsic curvature to be and notice we've made use of gamma. That's at gamma, which it's not only the hypersurface, the metric inducing the hypersurface. Once we restrict to coordinates that hypersurface, it's also a projector. So we're using it to project the result of taking the gradients of the vector n to the hypersurface. So this by definition is, if I replace what I have for gamma, this will be gamma CA so we're going to use this kind of massaging back and forth between the gamma and the metric plus n a lot today. So let's just do this. That is a simple one. So this will give me just back this one, and this will give me NA and C and B. And this is the acceleration of the vector n. So of course, if the vector n happened to be geodesic, this is 0, and we have this is simply the extrinsic curvature. If not, there is a component contribution from the acceleration. So now let's try and look for a few more properties that this tensor k that we have introduced satisfies. So in particular, k is symmetric. So this a priori is not obvious, but we can think of again. Let's introduce yet again this this way. So you have this vector normal here. We define the vector ddta the way we mentioned. This is just a vector tangent to that line that allows us at that point to define the vector that later on we're going to call the time evolution. But let's introduce another one, t twiddle, such that the gradient of t twiddle is exactly given by NA. So the relation between ddt and n, there is a overall difference given by the shift. Let's just imagine this t twiddle is exactly tangent to that n. And at that point, we have that relation. So KAB, and the way we define it is just gamma CA, C and B. We're going to replace that by the vector, let's call this, CB. And at that point, because we're on that hypersurface, because we're contracting with the projector, then CB is nothing but the gradient of this coordinate t-twill. But because it's just a gradient of a function, this commutes. So this is the same as I use it once again. And this is K BA. So the extrinsic curvature is symmetric. And there is one more thing we can do, is we can try and write K in a slightly different form. So let's consider the Lie derivative along the vector n of gamma AB. So let's just work what this is. This will be, let's see. So let us expand this a little bit. So now I'm going to go back and use the relation quite a bit. So this is NC, C. So let's write this in terms of the metric and the normal. I'm going to do that here again. And so let's scratch out things that are 0. So this is 0, because we're just taking the covariant derivative of the metric. This is 0, because we have NC grad of NC, and we say that N is, has a unit normal. So that's 0. Well, this contracted is 0, of course. And also this one, for the same reason. So now, let me try 2 more lines here. So now we're going to have NC grad C of this. And this we can write it, well, we can use Leibniz. So first we're going to be acting on this one, and then on that one. Let's do that. Because now when I use this one, I just simply lower the index here and over there. So I have So now I'm going to write, so I have NB here and I have NC there. Similarly here. And just as I've done before, so if I can write this in terms of both gamma and G. So I'm going to replace this by gamma CB minus GCB. And I can distribute this. Let me just write it here. So the first one, so I just pull the terms that have gamma first, and then use the metric to lower, to just contract the indices. So when I do act here, this C turns into a B, and this one turns into an A, but that let us simplify it. And so what we end up with is gamma projecting the derivative of n twice. So it's just nothing but minus 2 KAB from our definition. So this implies that we can also write the extrinsic curvature as the Lie derivative along the normal vector with a minus 2. So that's one useful relation, which we can make it more explicitly if we realize the following. The Lie derivative of n is in our property. In general, for any function phi, because n is orthogonal to gamma, this is true. This you can convince yourself by, if you want, redefining the vector n by phi and just acting with it. And every time, so for instance, if I got phi n here, well, in the definition, when I pull n out, I'm going to have a contraction that is 0 because gamma and n are orthogonal to each other. The reason I bring this property up is because this is, I can show the following. Right, we have this relation. So now I'm putting the lapse in here and dividing by the lapse. And then this, using our relation, where was it? Here, between d dt and n. This is the same as so the Lie derivative along t of gamma is nothing but dt of gamma. So the rate of change. So this allows us to rewrite and what I've done here rather quickly is I change my A's and B's into I's and J's. So what I have done here is just begin to use explicitly coordinates where labels I's and J's are intrinsic to the hypersurface. And this label A and B are coordinates that run from T all the way to the space coordinates. But if you check what T is and Ti is 0. So we're just making explicit that the only thing that survives are things related to the space hypersurface. So this is another relation. You can expand what the Lie derivative is. And so then you can write so we can write it this way, we can write it that way, and in particular, this we may use later on. So here I just expanded what the Lie derivative of beta is. It's going to be, it's this. What I have yet to tell you is what this d is. So this d is a covariant derivative associated to the gamma metric. So d I of gamma jk is equal to 0. So as an exercise, rewrite this in terms of partials, and then you're going to find a different way of writing this equation that does not involve the d, but involves partial derivatives. So we work hard to have a partial derivative here with respect to time, do the same thing, and this, you're going to end up with a very simple expression. So far we have done nothing but introduce concepts that are mainly kinematic. We have yet to bring Einstein's equations at all. So let's try and shoot there. We want to rewrite Einstein's equations in a way adapted to this foliation that we have introduced. And for that, let me just give you a few definitions, tell you where they come from. So the first one I just mentioned is that one. So let me just write it here. There's a d is a covariant derivative to a hypersurface. Of course, how does the actor is defined? Well, the covariant derivative of a 3 tensor, let me just call it this way, that is projected, as a result of the projection, the full 4D tensor onto the hypersurface is by definition the projection of all the components of the derivative. So let me just write it this way. Right. So in the full spacetime, we know how to take that one. That's a standard derivative of a 2 tensor. And the full projection of that gives us the action of the covariant derivative associated to the metric of the foliation of the tensor T, which is a tensor associated to the foliation. So sometimes we'll just know this by a 3, because this has been the projection of this T onto the hypersurface. This is how we're going to interpret, or we can compute what the operation of that derivative operator is. And we're going to use it now quite explicitly. So the first thing is to recall a couple of relations. So one is the Gauss-Kodachi. So we're not going to derive these. I can tell you where they are. But it's a relation that gives us a way to tie curvature tensors that we compute in the hypersurface with curvature tensors that we compute in the full space. So the Gauss-Kodachi equation tells us that if you take the full Riemann tensor, now let's project the full Riemann tensor. So I'm going to need fully projected. So I'm going to need 4 projecting tensors. Oh, sorry. Here I switched notations. Sorry about that. H and gamma are the same for me. So I'm going to have 4 gammas. So I'm contracting each one of those. So just to keep simple the right-hand side, let me just label this as A1, B1, C1, and D1. So this is going to be A1, B1, C1, D1, A, B, C, D. So the relation tells us that this is nothing but so what we do is, if we take that metric of the intrinsic hypersurface, we compute its Riemann tensor, and combine it this way with the extrinsic curvature tensors, the result of this is the Riemann tensor of the full spacetime projected onto the hypersurface. So remember, this is purely spatial. The extrinsic curvature is spatial. So if I multiply this KAB by n, I get a 0. Why? This I didn't say. Let's take this definition, multiply by n, let's say on B, let's contract on B. So then I have an NB grad C of NB, but that's 0 because then it's normalized. Multiply n by the first component, NA, KA. Well, but then NA is multiplying gamma, and gamma is a projection, so we get a 0. So K is a purely spatial vector. So again, this doesn't tell you a relation of all components of the full Riemann tensor. This only the projection of the spatial part of the Riemann tensor can be written this way. But we also have two more relations. So let me just give you the first one. This is known as the Codazzi-Mainardi equation. And now we're going to project three components, three of the indices, and along orthogonal to the parallel to the hypersurface, and one orthogonal. So let's start again. So this tells us that if we contract one of them parallel to the normal to the hypersurface, and all the other ones at the tangential to the hypersurface, we can relate it with their covariant derivatives of things that live on the hypersurface. So even though we took one of them parallel to the orthogonal vector, the net result is something that lives completely on the hypersurface. So this is at sigma. So at any sigma, this is true. So the other thing we can observe with this relation is that even though we know the Riemann tensor contains second derivatives of all metric tensors, these particular projections contain no time derivatives, or no second time derivatives of the metric. Because this is the Riemann tensor of the metric gamma on the hypersurface itself, so there is no time there. So this contains only at most second space derivatives. And these are the extrinsic curvatures which we define, which at most have one time derivative. And similarly here, we have one time derivative at most, and we have the covariant derivative on the hypersurface. The other observation is, so we have no second ddt. We also have no explicit appearance of lapse and shift. So if anyone hands us some metric gamma and some extrinsic curvature, we can compute this. We don't need to know what happens, how this particular foliation is embedded in the rest of the spacetime. So let us now try and go in the direction we wanted, which is to try and connect or bring Einstein's equations at some point. So let's think of what happens if we take the following. So I take the full Riemann. I contract with this metric tensors. So by definition, this. So let's see what happens. If we have G and G acting on RABCD, that's just a Ricci scalar. If we have one G and one N, we have the Ricci tensor multiply contracted by the ends. Right, we get 1 from this, and the same with this R1. And if we have the 4 ends, then we have a 0 due to symmetry, the antisymmetric character of pair of indices of the Riemann tensor. But this is nothing but twice of GAB, right? So we call the Einstein tensor GAB. So now what we can do is just, let's go back to the Gauss-Kodashi equation, which has those gammas. We can multiply by appropriate G metric tensors to construct this object, right? If I contract an A with a B, then I will, well, an A with a C, I bring A1, C1, and similar with B1 and D1. So we can, by the appropriate contraction of that, we're going to get this component or this combination of the Einstein tensor. So from Gauss-Kodashi, we have implies okay, this is our first relation that links Einstein's equations in the full spacetime with something that now only knows about the hypersurface. So this tells us that if you take the full Einstein equations and contract it with the normal to the hypersurface, this thing, which a priori has all components, only knows about the hypersurface and the way that hypersurface is embedded in the larger spacetime. Remember we said this combination has no second time derivatives. So this is known once we include the right-hand side. So let me just do this. So from here, from GAB, we would also obtain the following. Right, we're going to use this result together with Einstein's equations. We are considering the contraction of G with two normal vectors. We can rewrite that projection in this way. So this says that the combination of the intrinsic curvature and the Riemann or Ricci scalar of the intrinsic metric to the hypersurface is equal to 16 pi rho defined this way. And what we're saying is n, remember, is a time-like vector, normalized. So this is nothing but the energy density measured by an observer that is tangent to n. So this is known as that's the Hamiltonian constraint. So any questions? So let me get to the other constraint, and then we look at the evolution equations tomorrow. Yes?
That k squared, that k, is it just GAB contract?
Oh, good. So K, AB, that is, so K is gamma AB. But it's also this one, because remember the difference between G and gamma is N, and K is purely spatial. So N contracted with K is always 0. So now we can notice the following. So this. So if I take gamma AB and raise one index with the gamma, and N contracting the second component, this is the same as considering gamma AB RBD. So why? Is because when we contract N with the component or the contribution to GBD that is given by the Ricci scalar times GBD, what we end up is lowering the index of D into B and contracting with gamma, so that's a 0. And the reason we want to consider this one instead is because we can use the Codazzi minority equation that is linking a projection of R, and when we consider that combination, we end up with a Ricci scalar written in terms of the difference of covariant derivatives of extrinsic curvature. So this from here, yes?
Is there an ND on the right-hand side?
AB, BD. Is it what?
Yeah, the D index on one hand is contracting, and on the other.
Oh, sorry. This should be.
An ND maybe.
This should be. D.
Or AD, yeah.
Thank you. So from Codazzi minority, this is equal to and so we end up with this relation. Right, because this I can rewrite as dB
something weird on the first because the B is not contracted on the right hand side on the B.
Since there's vector n on the right hand side.
Wait.
Yeah, I think you just want the n vector on that side too, right?
Yeah, I forgot the n. Yeah. Yes. Forgot the n. Where we are? Where? So here is the next equation. So if we introduce J as the appropriate contraction and projection of the stress energy tensor that we may have if our spacetime is non-vacuum. The second relation, we can use the Codazzi-Marinardi equations to write another subset of Einstein's equations in this way that only involves, once again, derivatives on the hypersurface and a source on that hypersurface because we have projected. And the same observations applies. We do not have second time derivatives, and there is no explicit appearance of the lapse on the shift. And this is known as the momentum constraint. So any question? Now let me just write for tomorrow one extra relation. So in keeping of trying to get different components of the Riemann, the full Riemann tensor projected in different ways, the one we're going to use is the following. So we had the Gauss-Codazzi is one where we projected all components onto the hypersurface. The Codazzi-Marinardi is one where we projected 3 of them on one tangent to n. Now let's consider one that is 2 and 2. So we have gamma And this is as far as we can go, because if we were to project 3 along n, we would get 0 again by virtue of the symmetries of the Riemann tensor. So this is all we have to worry about. So the only thing we haven't considered is this one. This one will have hidden it a rule to tell us how the extrinsic curvature will change from one foliation to the other one, the rate of change. Notice it will be, at least it's showing explicit dependence on the lapse. And in here, we're going to have the rate of change. So tomorrow, what we're going to do is work with this equation and end up finally writing the full system of equations in terms of a kind of a geometric dynamic picture where we would, where we'll be thinking back on our spacetime and our foliations in such that on each hypersurface, or in a given initial hypersurface, we're going to consider that someone is providing this data together with some way or some specification for the lapse and the shift. And the equations of motions are going to, these equations are going to tell us the constraints, the momentum and Hamiltonian constraints will tell us relations that these objects will have to satisfy in order for this to be consistent with Einstein's equations, give initial data that is consistent. We're going to show that this extra equation will determine how this changes in time, how this changes in time. We already know how this changes in time by virtue of the definition. We're going to establish that how those equations are going to be such that if the constraints are satisfied at this hypersurface, and we evolve K with this equation, the constraints will be satisfied at an H hypersurface automatically. And that's what we're going to cover tomorrow. I'm going to stop here.